All right, wonderful. Well, good morning, everyone. Thank you all so much for coming to the talk this morning. I'm Carly Randall. I come from the Australian Institute of Marine Science, and I'm really excited to be here today to talk to you all about some of the learnings that we've gained over the last 5 years of research in the area of coral seeding. I'd also like to acknowledge the traditional custodians of the lands on which we live and work, and pay my respects to elders past, present, and emerging, and also extend that acknowledgement to any First Nations people who are in the room today with us. So as we've seen throughout the week, many of the projects that have been presented at the symposium are really the result of really large partnerships, and ours is no exception. This is the wonderful CAD team. I'm presenting this work today on behalf of all of these fantastic collaborators, so I wanted to acknowledge them here. Considering the RAP program structure, we fall within the Coral Aquaculture and Deployment Subprogram, and our aim is really to undertake the research and development to produce pipelines from the aquaculture facility to deployment of coral seeding devices at scale. And we have a 5-year goal of being able to deploy over 1 million seeding units per year. So our program feeds back into all of the cross-cutting programs of RAP, but in particular the translation to deployment cross-cutting program, as well as the modeling and decision support. So the translation to deployment team, they're really operationalizing coral mass deployments. And then the modeling and decision support teams we're feeding data to them, and they're feeding information back to us in terms of making deployment decisions about where best to deploy and when to deploy. So the approach that we're taking to undertake coral seeding at scale comes from the terrestrial world of reforestation. They use an aerial reforestation method that we're trying to adapt. And the approach looks something like this, where you have a seedling that is established growing on a substrate. That substrate is then inserted into a carrier device that has some protective features that can enhance the survival of that seedling. And then those are released over degraded habitats from the air, or in our case, from vessels at the surface of the ocean. And an important component of this is that the deployment of these devices is really information and technologically driven. So at a really high level, our coral seeding approach begins with a modular production of corals in the aquaculture facility. So we've designed these sheets that you see here at the bottom. They have modular units, and Michaela Nordberg will be talking about all of the aquaculture facility components of this research later today. So I'm just gonna kind of skip over that for now. The second step is to then transport those corals to site at very high density transport systems. The idea is then to assemble the seeding devices at the surface on site of deployment. And so the pink sheet there is actually broken up into modular sort of units or tabs. Those tabs are then inserted into a carrier device, and that is then what is deployed from the surface. So what I'd like to do today is talk you through 3 focal areas of research and development that we've done in the CAD sub-program over the last 5 years. So the first of those 3 areas is in the optimization of that seeding device design. So what should that device actually look like? And that's really informing our understanding of the what in terms of coral seeding. The second focal area is all about trying to understand what the environmental drivers of survival and growth are for these corals, and to do this across taxa. And so this is informing our understanding of who, so which species we should be deploying, and where it's best to deploy those. And then the third focal area is intended to allow us to start figuring out how best to upscale this deployment to the millions of corals per year, and that's getting at the how of coral seeding. So I don't have a whole lot of time to give you deep dives into each of these areas, so what I want to do is just highlight a couple of key studies that explain to you all the evolution of the thinking in each of these 3 areas of R&D. So the first one will be about optimizing that seeding device design, and it's important to say at the start that 5 years ago, we set out a list of key device design requirements. So these were kind of non-negotiable things at the start that constraints we had to work within. That first one is that the system has to be modular. We had to separate the settlement surface from the deployment device. And the reason for this is because space equals money. In an aquaculture facility, it's very expensive to keep these corals alive. And all the modelers who are working on this were telling us it's simply not feasible if you want to settle on the same devices that you deploy at mass production to do that. It's simply too expensive. And so in the method that we've developed, the corals are maintained at very, very high densities in the facility during transport and prior to assembly. They also need to be conducive with automatic processes. We also needed the devices to be able to lodge into the reef matrix and to minimize their movement. We need to be able to achieve high survival above background rates. And the devices, of course, need to be environmentally acceptable, readily manufacturable, and easily transported. So a couple of the key questions in this space at the beginning were, okay, well, what's the best shape for this coral seeding device? What's the best orientation in which to put the corals in the device? And how can we protect those juvenile corals from the pressures they face once they're seeded on the reef? So I'll talk you through a couple of key studies now that we've done. And the first one is led by Beck Forrester and her team, where she took a very early device design, which you see on the right, and looked at how the shape and size of that device influenced the retention of the device on the reef. So she deployed these devices, divers deployed them in large plots on the reef. They were imaged, and then they were revisited every 3 months, and the movement of every individual device was tracked over a year's deployment. And what Beck's team found was that the overall displacement of devices of all 4 of those designs moved less than 20 centimeters from the point at which they were deployed. And then that movement declined even more after about 6 months when the devices started to become cemented into the reef framework. She also found that the devices with an intermediate number of arms tended to move a bit less, although that wasn't statistically significant with these data. At the same time, Taylor Whitman was leading an experiment that was looking at how we can protect the corals from predation or grazing pressure. And so in this study, she used an older device design that compared corals in a control that didn't have any protection, which you see on the left there, with ones that did have protective features on the right. And what she found was that the exclusion device, the one on the right, increased survival significantly across sort of all life history stages and locations and positions in the device. And in some cases, that was survival that was doubled. She also found that side-facing corals performed better than top-facing corals, and that microfragments performed better than spat, and that was pretty expected. When she looked at this in terms of the actual grazing behavior of the fishes, she found that those exclusion devices really significantly reduced the grazing impacts on the spat. And she has this great photo that shows some of that grazing behavior. And shockingly, I think it was shocking anyway, she had over 90% complete grazing on the devices within 48 hours of deployment. So if we don't protect the recruits, they will not survive these pressures. But you'll also notice in these figures that there was much higher grazing at some sites than others. So it is also site-specific and depends on the communities that are on the site of deployment. Moving south, Kathy Page led a deployment in Wahab Sea country, comparing how well corals in side-facing positions did with corals on the underside of the devices. She did this with 3 different taxa deployed in Wahab country over a year, and found that the side orientation performed better than the bottom-oriented corals across all taxa. The reason for this was just owing to light limitation. There was just not enough light reaching those corals on the undersides of the device. So fast forward a year, the device designs that you see at the top of this figure were kind of the next generation designs. They incorporated protection around the recruits based on Taylor's work. They also kept corals in vertical positions based on those earlier studies. And so Beck deployed these again looking at retention, and also found these devices really didn't move more than 20 centimeters from the point of deployment. That also declined kind of from 3 months on. But you'll see that there was an uptick between 9 and 12 months here in the device movement, and that was because we had some wet season storms that came through and moved some of those devices up to 6 meters from the place of deployment. But overall, the movement was pretty constrained to about 20 centimeters. Okay, so the evolution of our seeding devices kind of looked like this over the last few years. We have this modular system that has tabs that seems to work pretty well. The design that we're using at the moment is this one here on the right. It is a design that's also linkable so that we can actually make through more complex shapes so that these seeding devices on certain reefs could be linked if we have rubble and we're afraid the devices may fall through the reef framework. And so this is the device that we are moving forward with in terms of our research. Grazing protection is obviously really critical, and vertical orientation seems to be best across all the environments we've tested. All right, moving into the second focal area of R&D. So we'll shift gears now and talk a bit about the drivers of survival and mortality on these coral juveniles. So just wanted to give you a high-level summary first. To date, we have deployed 22 experiments in the CAD program. We've tested this across 13 species. We've tested across life history stages in all 3 regions of the reef. We've tested these devices both fixed and freely deployed, and our average yield, which is the survival at the device level at 1 year of age, is 40%. But obviously that range from 4 to 83% is huge, and it really depends heavily on all these factors: species, environment, the method of deployment. So some of the key questions in this space have been, well, what are the key environmental and biological drivers of seeded coral success, and at what spatial scale is the greatest variance in survival of corals explained? So I'll start first with a study that was led by Saskia Jurriaans. So this was an experiment where we deployed corals across a latitudinal gradient and a wave energy gradient. We had corals deployed up here at Moore Reef, in the central region at Davies, and in the southern region at Heron Reef. And within each of those reefs, we identified 10 sites that spanned a wave energy gradient. And we did that in collaboration with some modelers at Ames, Mari, and Ben. And so we asked, does this survival vary across the wave energy and the latitudinal gradient, and how does it vary amongst taxa? And so the results of this first year's deployment was very taxa specific. And so those relationships depended on what species we were deploying where, and also could be a result of latitudinal differences. Now, in this particular experiment, we couldn't disentangle latitude with taxa because we had to deploy the corals that spawned from that particular reef back to that particular site. And so we're still trying to get at how influential each of those variables might be in driving these responses. We repeated this again in 2022, just at Davies Reef, but with a larger number of taxa and also with spat and microfragments. And we again found that it was quite variable across taxa life history stages. And we also found that water flow doesn't seem to be a very good predictor of survival. So if water flow is not a good predictor, then what is? And the short answer is we're still looking into that. For this particular experiment, we are looking into the benthic community composition and other environmental metrics of the sites, the sedimentation, the temperature, and those things. Now, heading back down south to Whippleborough Sea Country, Kathy Page led a deployment that looked particularly at wanting to know at what spatial scale was the greatest variance in the survival of seeded corals explained, and could we identify any environmental correlates of survival? And so this approach took a really nested and hierarchical design. We deployed these 3 taxa across 3 replicate reefs, and in each reef we had 3 replicate sites. In each site we had 3 replicate transects, and in each transect we had plots nested. And what Kathy found after 1 year of deployment was that the highest variation in survival and growth was explained at the smallest spatial scale, so just 1 to 2 meter differences amongst the plots. That was true for survival and also for growth, and for all 3 taxa. So then we said, well, okay, well, are there any differences at that finest spatial scale in terms of devices that survived and those that did not survive? When we looked at the benthic community around those, though, you see in blue are the devices that survived, and in red are the devices that didn't. The benthic communities are really pretty overlapping. But we deployed at all three of our reefs. Where we deployed were similar community composition, similar features, and so we said, okay, well, what if we deploy at more sort of extreme environmental conditions to compare? So in the second year's deployment, we deployed at 3 coral-dominated sites and at 3 sites that were algal-dominated. And we did the same 3 taxa seeded to these sites, and what we found was that there was a lot of variability within groups, more variability within groups than between groups. And yeah, again, the survival varied by taxa. So if you look at Montipora aquatuberculata on the right, you'll see it really didn't matter if it was a coral or an algal-dominated site. It was something that was more specific to the particular site that was determining whether the corals survived. So again, we did this analysis looking at what the community composition was around devices that survived and didn't. There was a bit more separation here, and we saw that there was higher survival in plots that had branching and tabulate acropora present, unsurprisingly, but also where we saw Lobophora. There was lower survival in plots where we had a heavy cover of sargassum, red algae, and Paysonalia. And so what we think is happening here is that the presence of low-lying algae might be more able to allow survival of corals, at least for that first year, than the taller canopy-forming algae, which are probably creating more light limitation for those recruits. But again, if you look at these dimensionless PCA, it's still not explaining a whole lot of the variability. So we said, okay, well, let's hone in even further. We know this fine spatial scales are really important, so what about what's actually growing on the settlement substrate? And so Kathy also looked at this, and what we found was that in the short term and over the course of a year, the coverage of crustose coralline algae on the settlement surfaces really was related to survival. So the higher the CCA, the lower the survival. And I think, you know, that's because this CCA that we're using to induce settlement is also really competitive with the coral juveniles. It also illustrated to us that what communities live in the aquaculture facility on the substrates actually tend to remain in the field for quite a long time. And so what we do in the facility really matters in the long-term performance of those corals once they're seeded onto the reef. All right, so enter Jose Montalvo Prano and Andrew Negri and their team, who are trying to now address this using an antifoulant. So they've been testing this commercial non-biocidal antifoulant that is applied to the seeding devices. In that picture, you'll see the antifoulant coating is just in the center portion of the device, around where the coral recruits are located. It's not on the edges or the arms of the device, because we want that to be cemented into the reef so the devices don't move. So they've been testing this antifoulant, and they have found that the antifoulant in general increases survival by about double. It doubles the survival, and it's most effective in sites where CCA is a really dominant constituent of the benthos. Importantly, after a year's time, that antifoul still works pretty well to keep competition at bay, but there doesn't seem to be any toxicity. Those corals grow very easily over that antifoul coating. They just don't like to settle directly on the antifoul coating. So we're working at figuring out how we can apply this sort of near field to the settlement surface to keep competition at bay. Okay, so to summarize this sort of environmental drivers component of the work, we're really seeing differences at very small spatial scales, and I think that this has significant implications for our deployment decisions for seeding. Because if we need to make sort of in real time decisions about where we're deploying, we need to be doing that at pretty small spatial scales. Most of these experiments, the plots aren't very far from one another, but we're still seeing big differences in survival. So we need our sort of AI-guided decision making to be done at a sort of 1 square meter or smaller scale. Our trends are also species and life history specific. And competition and grazing are both significant drivers of mortality, but can be effectively managed with the design of the device and with some antifoul treatments. Okay, moving quickly into this final section, procedures for upscaling our deployment. So I'll just start with a high-level summary. Over the last 5 years, we've really seen an exponential increase in the number of devices we're able to deploy on an annual basis. So this is encouraging. But when we put this in the context of where we hope to be, it's still pretty far down there on the y-axis. Our aim is in 5 years to be able to deploy 1 million corals per year, 1 million seeding devices per year. So key questions in this space have been, can we deploy accurately from vessels? How does our surface deployment affect the survival of the corals? And can we increase our efficiency in assembly and deployment? So this past year was the first opportunity we had to actually test coral seeding from a vessel. We did this for about 1,500 devices at 2 reefs, and we deployed these from the vessel along pre-identified GPS tracks. We tested how well devices can be deployed when they're single and when they're linked together, how well the surface deployments work at 5 meters and at 10 meters, looking at accuracy. We looked at deployment from the vessels at 1 and 3 knots, and also the orientation of the devices when they're released from the surface. How do they land on the benthos, if they're stacked vertically or horizontally? And then, of course, all of these were compared with diver-deployed devices, which is the way we've been seeding to date. All right, I'll give you a quick idea of what this actually looks like. So this was one of the first attempts at seeding from the vessel. The surface deployer was able to deploy devices 1 every 1.2 seconds, and we were aiming for every 1 second, so it was pretty good. And you can see there's a single device there. There have been some linked devices. And so we had divers in the water then monitoring and evaluating how well those devices actually land on the seafloor. And the image on the left shows you the surface deployed devices, which are the white ones, compared with diver deployed devices, which have those black spindles in the center. All right, so what we found in this first trial was that 80% of those linked devices remained linked when they reached the seafloor, which is pretty good, although some room for improvement. We also found that the devices landed less than 1 meter from the transect that was laid out, and that was the case at both 5 and 10 meters depth. So we were really happy with the accuracy we were able to achieve with the deployments. And the accuracy was equivalent when the vessel was going at 1 and at 3 knots. The horizontal and vertical stacks landed similarly in similar densities, although the vertical stacks tended to disperse just a little bit more in space, but less than sort of 1 square meter, which is what we were aiming for. And the team is currently underwater at Davies Reef monitoring for the survival, so we don't have that data to present, but we'll have it in hand pretty soon. So another component of this large field trial this past year was to look at how well we could actually transport these tabs at high density and deploy them and assemble them at the surface and then field deploy them. So we were pretty effective at transporting the devices in these racks that were made, although the interior sheets had a bit of mortality, and I think that's owing to poor circulation within those transport systems. And so there's a lot of room for improvement there, just to make sure that we're housing these in the best conditions to keep them alive over the course of the deployment. We manually cut out 30,000 of these tabs. We have a hand cutter, which you can see in the picture in the center there. And that worked effectively with an assembly team. Thank you. But it was pretty ergonomically uncomfortable, and it was also sort of uncomfortable conditions. And so we did compare this with assembly in the aquaculture facility before transport, and that was more effective at the manual level. But what we're doing now is we have a jig that's currently being made that will allow us to upscale the cutting and assembly of the devices manually. And then further afield, we're working with a robotics team to actually put a robotics assembly of this so it can fully automate the process. Okay, the final thing I want to say about our deployment, so just kind of a shout out to another group within the RRAP program who's developing this deployment guidance system. So it's made up of this unit called Reef Scan, which has real-time substrate detection. It's a camera on the bottom of a pole, essentially. It goes at the front, the transom of the vessel, and then it's in real time detecting what the benthos is and then making decisions about yes, deploy, no, don't deploy, and sending that back to a dispenser. So the reef scan is working and it's being trialed now, but the deployment guidance system in its sort of final form is still being worked on, and Ben will be speaking about that more later today. Okay, so just to wrap up, I hope that I've given everybody a sense of all the R&D that we've done within the CAD program over the last 5 years. We've really honed in on these sort of 3 areas, and yeah, we'll continue to work in this space in RAP version 2 and try to get this working at scale. So thanks so much.
Hello. Yeah. Amazing, Carly. Does anyone have questions?
Carly, in the upscaling, what would be an acceptable level for it to move into pilot deployments? What acceptable numbers?
Right, yep. So we have a plan over the next 5 years that starts with 100,000 devices next year and then goes up from there, 200,000, 400, 600,000, and then 1 million in the 5-year mark. So that's what we are aiming for. Not all of those will necessarily be deployed by us as researchers, though. We'll start integrating traditional owner-led deployments and tourism-led deployments in that process. So there's a 5-year plan to roll that out.
Any more questions? Yeah.
Thanks. Hi, Carly. Can you say anything about the attachment of the colonies off the devices onto the substrate? Have some of them been in long enough to sort of look at the time scale of that and the effectiveness of that?
Yeah, that's a great question, John. Thanks. So as I mentioned, we've been testing this with recruits and microfragments. The microfragments, as you might expect, will grow off the devices much faster than the recruits. Within 6 months, the microfragments will grow off the device and onto the reef substrate, and so the cementation of the device by the CCA and the coral kind of happens simultaneously in that case. The recruits take a bit longer to grow off the device, but the tabs are about 11 millimeters by 11 millimeters, so if those recruits settle near the edges of the tabs, they actually don't have to go too far to reach the substrate. So we're seeing some within 1 year start to grow off the device, but it kind of depends on the growth rate of the spat and the site as to how quickly they'll grow off.
Same question, actually.
Thanks, Carly. Can you give us an indication of what a single device costs?
Too much at the moment. I actually don't have those figures at hand, but I would guess that they're a couple dollars a device at the moment. And so this is something that at scale will become cheaper. And so we're working to try and identify manufacturers that can do it more cheaply when we start talking about sort of 500,000 or 1 million devices per year. The goal is to get them, all components included, the settlement, substrate plus device, to be less than $1 per device.
All right, thank you, Carly.